notes. Okay, so I hope you all are able to see the screen.
Yes, sir.
Fine. So this is the problem that we had to start off yesterday, where we had just left. So we have a geostationary satellite, which is located at about 90° west. Okay, and calculate the azimuth angle for an Earth station antenna at latitude 35 degrees north and longitude 100 degrees west. Always keep in mind south and west will be taken as minus, okay, as we saw yesterday. So they're asking us to find out the azimuth angle. So these are the quantities here. Okay, so just a moment. So these are the values here. Phi SS is the longitude, okay, which is about minus 90°. Okay, so we have 90° west, so we're taking as minus 90°. And so 5 lambda e is 35 degrees because it's north, and your 5e is minus 100° because it's west. And then we have the formula, right? B is equal to 5e minus 5ss. So which means it is minus 100 minus of minus 90. Okay, minus 5ss, so minus of minus, so you get plus 90, so which is nothing but about minus 10 degrees. Now we start applying the cos formulas. So cos of b, cos of b, so b value we have, which is minus 10. Okay, and lambda e, okay, lambda e is 35, then cos b into cos lambda e. Okay, so these two we multiply, and then mean the cos values, and then we get about 0.8. Okay, now similarly, okay, what we have to even do is they have told us to calculate a and then az, right? So we have the formula E is equal to sine inverse, okay, sine modulus of b and sine b. So here, okay, So what we can do here is, hmm, so we are using this formula here. Okay, B is equal to 5E minus 5SS, and B is equal to cos inverse of, okay, cos inverse of cos B and cos lambda E. So this small b is what I have obtained here. So that's why it's important for you to note down the formulas. Okay, and this is how I got my small b. Capital B is this. Fine. A is equal to sine inverse. Okay, and yeah. So I just substitute those values. Okay, since it's a modulus. Okay, so I take plus or minus. So I just take the value and divided by sine b. So b value we have seen that it is 36.23. So just look into the values. Okay, and we get about plus 17 degrees. Okay, now remember we had another information, right, where we had to see if lambda is greater than 0 and if b is less than 0, right? So this table that I'm talking about, lambda e and b, okay. So greater than 0 and less than 0. Okay, so what we have to do, we have to use this case 180 degree minus a. So that is what we are going to use here. Azimuth angle is equal to 180 degree minus e. Okay, so your lambda e here is how much? 35, so greater than 0. And your b, okay, uh, the b value, okay, which is cos. So we are getting about yeah, sine, so about minus 0.17, so which is less than 0. So if we calculate this 180 degree minus a value is here 17, so we get about 162.9 degrees. So the only thing here that you have to remember is this conditions. You have to check what is your lambda e and what is your b and what you have to do to calculate your azimuth angle, and most importantly these formulas: elevation angle, d, then your a, capital B, small b. So these are the a few important things. So 1, 2, 3, 4, 5. So 5 formulas here, 5 formulas, and then a tabular column. So if you know this, and most importantly, you should know for west and for south what we do. We actually change the um, notation, right? We change the, uh, we actually put it as minus. Okay. So we will see one more here. Find the range and antenna elevation angle. So here they are making use of EL's formula. Okay, elevation angle for the situation specified in the above example. So which means we are continuing the same example here. Okay, same values: 90 degrees west, 35 degrees north, and 100 degrees west, and we are finding the azimuth angle. Okay, in this problem. But here what we are doing is we are using the radius of the earth, then AGSO is so much, which is nothing but the radius of geostationary orbit, and value of b we have actually seen previously, right? Value of b. So the same thing we are continuing. This is just like part 2 of the same problem, and here we are to find out the range and uh, antenna elevation angle. So these two are to be found out. So we will start extracting data from the problem. R is equal to so much, then AGSO, then B, then we have the formula D. Why do I want D? Because I have it in my elevation angle, right? Angle of elevation. So what is my EL? See, in EL I have D. So first I have to find out what is D. AGSO value is already given, B value is there, so this is the only value that I need, which is B. R value is given, AGSO value is given, right? Then R is there, AGSO is there, B, small b is also there, right? So we have all the values. So once I find out D, the distance, okay, from the center of the earth to the satellite, okay, then it's easy for me to find out the angle of elevation, which is EL. Okay, and yeah, so I have the radius of the earth. Okay, the values are given 6371. Okay, then the other values are also taken, which is 42164, and then the value of B is also 36.23. That's also taken here. So it's all about, the problems here that you see in satellite communications are all standard. Okay, the only thing is you will have to know the formula properly. So if you know the formula, you can substitute and get the values. And sometimes, okay, the most common mistakes that I have found in few students is that they don't actually put minus for this. Okay, that is where the whole thing changes. See, if you just change here, okay, if it's not minus, then it becomes minus 100, minus 90, which goes about minus 190. So your whole value is changed. So if the b value has changed, okay, all these values also does change because it's all interdependent, right? So attention to detail is very much needed. So finally I find out that my angle of elevation is about 48 degrees. Okay. So now moving on to polar orbits. Okay. So polar orbits, as I told you, these are not like your geostationary orbits which have 0 degree inclination, but then these are inclined approximately about 90 degrees from the equator. Equator is just like, if you slice your earth, so what plane you get, that's the equator. They cover polar regions from North Pole to South Pole. So these polar orbits are helpful for us to in covering the polar ice caps. Now, was that possible with geostationary orbits? Covering the North and South Pole? Was those available? Could we cover? Students respond. Was it possible for us to cover the North and the South Pole using the geostationary orbits?
I guess no, sir.
No. So that's the reason we are actually looking at the polar orbits. Okay. So polar orbits will help us in covering the North Pole and the South Pole, the ice caps. And that is why you see that it is exactly 90 degree, because I need a straight line, okay, from the center of the earth downward and upward. So that creates an exact angle which is about 90 degrees. Okay, fine. So they take approximately about 99 minutes to cover one orbit around the earth. Okay, so about 100 minutes, okay, 99 to 100 minutes it takes in order to cover the earth. Okay. So going around the earth about less than 2 hours. Next you have the sun synchronous orbit. Okay, so that's one of the examples. We will be seeing that in the upcoming slides as to what is your sun synchronous orbits. We have seen that previously, right? Sun synchronous. Can someone tell me what is a sun synchronous orbit? Yeah, sun synchronous orbit. Okay, so you have the sun, okay, and then you have the line of nodes, and then this is how your angle changes with respect to Earth. Fine. Fixed angle between Earth and Sun line and orbital plane of Sun is called Sun synchronous orbit. So you'll have to take the Earth, you have to take the Sun and the orbital plane of Sun in order to create an um, angle. So in that angle, it goes around, and that is nothing but called your Sun synchronous orbit. Okay. So that is what we can see here. There's an angle that gets created with the Earth, with the Sun, and the orbital plane of Sun. Okay, so that is called a Sun synchronous orbit. Fine. These orbits every time pass a location on Earth at the same local time. So it is just like 3 o'clock, 3 p.m. which position it is next day. Okay, it will be in the same position at 3 o'clock. So which means the motion is constant. The movement is constant. Sun synchronous satellites pass through poles, also keeps changing its trajectory through Earth. So that is what we saw, right? So it helps us. Sun synchronous orbits actually keeps in sync the Earth's and the Sun's plane. Okay, and a certain angle is created. So that involves with regards to your orbit that gets created, and that subsequent orbit is called your sun synchronous orbit. Right. So next about your polar mount antennas. So antennas which are placed in the polar orbits are called polar mount antennas. So that's the explanation that you can see here. A polar mount is a model mount for satellite dishes that allow the dish to be pointed at many geostationary satellites by slowing around one axis. So there is a slight angular displacement. Okay. So this is nothing but your lambda e with respect to north direction. This is your r. This is the radius of the Earth. And this is your equatorial plane, as I told you. If you slice your Earth, okay, across east to west, okay, so that's your equatorial plane. Okay, then you have your antennas placed exactly at 90 degrees from the north. Okay, so that creates something called polar mount antennas. The antenna pointing can only be accurate for one satellite, and some pointing error must be accepted for satellites on either side of this. So instead of having 90 exact, okay, I can probably configure it in such a way that it is about 93. Sometimes it should accept those 2-3 degrees plus or minus 2-3 degrees, or probably 87. It should be able to accept and take up these minute errors. Okay. So if in case I don't have this tolerance, then what is going to happen? I'm going to lose out with signals, right? Because it doesn't point out, and if there is no tolerance, then we are going to lose out. It is just like you have an electrical circuit, and in this electrical circuit, if it's not manufactured in such a way that it accepts 240 volts or probably 300 volts, then when there is a slight fluctuation, okay, 240 to 280, it will withstand because it is made for about 300 volts, right? So it's always nice to have a tolerance, right? So the angle between polar mount and local horizontal plane is set equal to the Earth station latitude lambda e. Okay, so as we saw, this is kept in the north, and with the Earth latitude, okay, Earth station latitude lambda e, it is made, it is set right, making both sides lie parallel to the equatorial plane. So it should be aligned with our bore sight. Bore sight means the angle in which we are seeing. So you can see here the dish of the antenna is mounted on axis termed as polar axis, such that the antenna bore sight is normal to the axis. Okay, so this is placed in such a way that it is normal to the earth has rotated. Okay, the earth has rotated a certain degree, so this is in parallel with our line of sight of antenna, so that is your bore sight. Okay, straight to the antenna's path, it's called bore sight. Now the axis is tilted at an angle delta, which is relative to polar mount until the bore sight is pointing at a satellite position. So again, there is another new formula here, which is 90 degree. 90 degree why? Because we take it with respect to north 90 degree, and you have angle of elevation, okay, and your earth latitude, okay, lambda e. So EL, okay, which is the angle of elevation, is required for finding out where the satellite is, right? So if you can remember the diagram that we just saw previously, just bring up the diagram. Remember, we had a diagram which actually spoke about the center of the earth and the diameter d, right? So that was where we actually saw uh, as to how, yeah. So the center of the earth and the angle of elevation. Okay, so this is with respect to point A, center of the earth, and satellite. So elevation, as your satellite moves to an upper level, your angle of elevation also does increase. Okay. So that's about your angle of elevation. So that is required for finding out the uh, position of the satellite. Now see here, look at the diagram. Now here in this diagram, actually the earth's proper orientation is this line. Okay, so we are taking a perpendicular line in the point at which the antenna is placed. Okay, and we are drawing a normal line, perpendicular line. Okay, so that becomes our local horizontal plane. So this is my local horizontal plane. So the angle of this, okay, so that is your 90 degree with the north plus delta plus lambda e. Okay, so your 90 degree and your angle of elevation, how much angle it creates, okay, and then your lambda e, which is with respect to local horizontal plane. What is local horizontal plane? You are considering this straight line, okay, and even though there is a small tilt that has happened, but the original line is actually this, because as I told you, the earth is tilted about 23.5 degrees, right? So that is why we can see this line and this line separate. Okay, so if the earth is not tilted about its axis about 23, and if the tilt is 0, then we can see that these two lines will be on top of each other. Okay, so students, are you understanding what I'm trying to say here? Is it clear? Suhas? Suhas, you're following? Pranay, Likit, Suhas has answered. Thank you. Fine. So this is about your polar mount antennas. So the elevation angle is given by cos, and then we have AGSOD. So if I'm taking it, so if I have to find out t, then you know, right? It is square root involving the radius of the Earth as well, right? And cos b. So these formulas needs to be remembered. And what are the uses of these antennas? Polar mount are popular with home televisions. Okay, the ones that we are using right now, which are used to pick up signals and transmit, wherein we directly get connected to the satellite, right? So that's the reason we moved on from an analog to digital part. Okay, digital transmission, where the transmission becomes more clear. Okay, and you can also see here that the systems where they can use to access TV signals from many different geostationary satellites. So not only from one satellite, can get connected to different satellites because it is across north and south. It is not across east and west. So it's across north and south. So it can connect to different, because your geostationary satellites are actually towards your east and west. So they can connect, okay, because it's in the opposite direction. We have something called limits of visibility. Okay, limits of visibility. Now there can be uh, some scenarios where just like an eclipse, solar eclipse, lunar eclipse. Okay, where the sun goes invisible and the moon goes invisible, comes in between, right, and the shadow is falling on Earth. So that's about your limit of visibility. So here, if you can see, okay, there is east and west limits on the geostationary arc. So your satellite, okay, has some kind of limits. It is not that 100% it can cover, because our Earth is ellipse, right? So it cannot cover fully. There is east and west limits. These limits are set by geographic coordinates of the Earth station and antenna elevation. So the lowest elevation is 0. Okay, so in theory, but in practice, to avoid reception of excess noise from Earth, some finite minimum value of elevation is issued. So we cannot always maintain the ideal values, right? As I mentioned previously, there should be some kind of tolerance, plus or minus tolerance. So you can see that from the center of the Earth there is an AGSO here, which is nothing but your radius of geostationary orbit. Okay, and then you have another radius. Of course, both are going to be the same from the center of the Earth, and this is your geostationary orbit, which is just around the Earth. Okay, to avoid reception of excess noise, yes, we have seen that to estimate these limits, consider an Earth station at the equator. Okay, so we will just consider an example with the antenna pointing either west or east along horizontal as shown in the figure. Okay, so we have the antenna which is pointing this direction and the other direction also. So what are the limits that can happen? Okay, so we will have to use this formula, okay, where the radius is, you're going to take the arc cost value of uh, A and AGSO, right? And when we calculate, okay, so when we calculate, we are getting about 81.3 degrees. Okay, 81.3 degrees. Now this is nothing but 421646378. These are all standard values. Okay, if you can see, we had seen them in our problems, right? See, AGSO value and your R value. Okay, these are all standard values. Okay, so when we put them here, you're going to get about 81.3 degrees. So which means um, they are bounded to only about 81.3 degrees. Beyond that, not possible. Okay, so Earth eclipse of a satellite. Okay, so the satellite also can get into an eclipse. Okay, just like if you can remember the Chandrayaan program by our country, right? For about 7 to 8 minutes, they told that it's not in touch. Okay, there is no communication. So because that is a limit of visibility. So similarly, a satellite can get into an eclipse. A satellite is said to be in eclipse when the Earth or Moon prevents sunlight from reaching it. So, in this situation, what is going to happen? They will not have any solar power. They will have to use their own batteries, inbuilt batteries, because there is no sunlight falling on it. Solar eclipses are important as they affect the working of satellite, and particularly the energy that gets generated by solar cells are greatly affected. So these days, what is happening? Lithium-ion batteries were used. Okay, now they are trying to use lithium cadmium batteries. Okay, and nickel-based types of batteries. So lot of technologies, lot of enhancements are actually happening with regards to battery technology. To give you an example, I was just reading a research article where they have tried to get or generate fuel cells or energy with the help of spinach. Okay, the greens that we get in the market. So using these green leaves, they are able to generate energy. So like this, lot of research is actually happening with regards to battery because they play a very important role. When you buy a electronic gadget, you always want it to last for a long time, right? Between charges. So approximately we expect about 8 to 10 hours between each charge, or at least a significant 5 to 6 hours. So if in case you have to charge your laptop every half an hour, it becomes troublesome, and uh, customers wouldn't want to do that, to be always plugged into the power supply. If not, the meaning itself is gone, which is called as laptop, right? Okay, so a lot of technologies, lot of enhancements are happening in this regard. Okay. For geostationary satellites, the solar eclipse due to Earth occurs two periods. Okay, so one is 23 days before equinox. So equinox, this is a whole different concept, the equinox. Okay, so I will explain that in the upcoming classes. So this happens March 21st and about September 21st. So March 21st and September 21st are the 2 days where equinox. Okay, equinox is going to happen, where you can find that it ends 23 days after equinox. Okay, the geometric positions of Earth, Sun, and satellite during the eclipse are illustrated. So you can see here. Okay, okay. So you can see that you have the Earth's uh, north direction. Then you have the satellite in eclipse, which means it is not actually getting the sunlight. Why is it not getting the sunlight? Because it is here behind the Earth. Sun rays are coming here. Okay, so the sun rays are maximum getting dispersed at this angle. So if it's exactly behind Earth, okay, you will not get the sun rays. So which means these have to rely on their own solar cells, on their own inbuilt cells. Okay, so which means we have to develop these batteries in such a way that they will be able to sustain, okay, sustain the energy till they get back the sun rays. Okay, so a lot of enhancements, a lot of things are actually done with regards to this battery technology. Okay, so yeah, I think we will see this point as well. Okay, as to how uh, just a moment. Yeah, as to how and how long it's going to happen. So the eclipse lasts about 10 minutes and increases to a maximum of about 72 minutes. So which means your battery should be able to sustain up to 72 minutes, okay, for a full eclipse. And then the solar cells of the satellite become non-functional during the eclipse because they have to rely on their own batteries, right? So Earth eclipse of a satellite east. I think maybe we will stop here. Okay, Earth eclipse of satellite, and then we will continue in the next class. Okay, so just give me a moment while I share the attendance. Uh, you can actually look into your chat box. I have posted it. Okay, you can start giving in your attendance. So I think we'll stop here and we'll continue in the next class. Okay, thank you.